Hi guys, I welcome you to my YouTube channel. Today I had some free time and decided to record the practical which my students recently did. IBM is my name, and today I would like to take you to Advanced Practical Skills AS Physics 970. The paper we are going to record today is paper 34, component 34, May-June 2023. So you can check it out. If you're a teacher, you can download the question paper print for your students. Uh, Print also the confidential instructions so that you can know the apparatus that were used for this paper so that you prepare the practical for your students. Then maybe you can use my results as guiding results so that your students can know how to present their report or practical report or how to present their work in a practical. So without wasting time, I would like to take you to the question paper. So this is the paper, Advanced Practical Skills 2. This is May-June 2023. The paper is supposed to be 2 hours. So I'm going to take a few minutes to record question number 2. You are used to these instructions, so I'll go straight to question number 2. Okay, so this was question number 2. Having seen, if you have printed the question paper and you have obtained the materials, then we can start. So question number 2, measure and record the length L of the longer pipe as shown in the figure. So they were given two pipes, one was shorter, one was longer. So the students had an option. They could either take a repeated measurement here or they could take a single measurement because the pipe could easily be placed on the ruler for measurement. But I will take the results of my particular student who decided to show repeated measurements for the pipe because she argued that the pipe was not uniform. So I will draw a table for repeated measurements. You can draw a nice table, small table for your measurements. So she did the first attempt, L1 in centimeters. She did the second attempt, L2 in centimeters. So she just gave an idea that she had to repeat a measurement to obtain the average, but she produced the same measurement. So the length of the pipe was approximately 12 centimeters. So I expect if you follow the confidential instructions very well as the teacher, the length of the pipe is approximately 12 centimeters. So the average value of L here is 12.2. So this is 12.2 centimeters. All measurements in centimeters are recorded to one decimal place. Please do not forget the unit, centimeters. Then place the thermometer on the bench. Place the thermometer on the bench, record the room temperature. So room temperature, this was recorded once. According to the confidential, the thermometer to be used was having a precision of 1 degree to the nearest degree. So that means the readings should be whole numbers. So my student here measured the room temperature as 24 degrees Celsius. 24 degrees Celsius. The thermometer which was required in the confidential measures the nearest degree, which means all measurements of temperature are whole numbers. So that's what my student recorded. You have been provided with a wooden rod supported by a pin. Using a longer pipe, assemble the apparatus as shown. So my students assembled this apparatus. My student took a picture of this assembled apparatus, and it is what is on the front page of this video. It's what on the cover of this video. So this is how the assembled apparatus looks like. Adjust the apparatus so that the rod is parallel to the bench. If they ask you to adjust so that the rod is parallel to the bench, so there's a limitation here. It is difficult to judge that the rod is parallel to the bench, and the only way we can solve this is using a spirit level which has not been provided. Secondly, measure and record the height x1 of the end of the rod above the bench. So you are going to measure x1 from the bench to the end of the rod. So there's a limitation here in measuring x1. One, you are holding the ruler in your hand, so the hand cannot remain still when you're holding the ruler vertical. It It is also hard to know that the ruler is vertical when you're measuring x1. So that is a limitation. So there's a second limitation there on measuring x1. But then my student measured x1 and her value of, she took repeated measurements. I just didn't want the repeated measurements, but this one took repeated measurements. And these are the values that she obtained for x1. So because she took repeated measurements, I will draw a table for her measurements. It wasn't necessary to take repeated measurements at this point, but even if you take, you're not penalized for taking repeated measurements after all. So her first measurement, her first attempt for x1 in centimeters, she got 43.1. She tried to place the ruler again to get a second measurement or second attempt, and she got 43.2. So she got the average, and the average is 43.2 to the nearest millimeter. So it is 43.2 in centimeters. So it should be one decimal place in centimeters, the average. Then slowly pour boiling water into the measuring cylinder until it covers the pipe. Be careful when you are dealing with boiling water. Place the thermometer in the water, record the temperature. So my student placed the thermometer in the water and she recorded 67 degrees Celsius. 67 degrees Celsius. So that's what she got as she recorded as the temperature. Then remove the thermometer. Of course, I'm saying the thermometer which is required in the exam was measured to the nearest whole number. Most thermometers in the laboratory measure to 0.0 or 0.5, but this one was measuring to the nearest degree Celsius. Remove the thermometer from the water. The expansion of the pipe causes the end of the pipe of the rod to move down. The expansion of the pipe causes the end of the rod to move down. Measure the new height x2 of the end of the rod above the bench. So from this, when they poured here boiling water, the pipe was expected to expand and the rod was expected to move downward. So they had to measure x2 from in the same position where x1 is. So my student again tried to do a repeated measurement. So she drew a table. And I'm saying it wasn't necessary to do a repeated measurement here, simply because the ruler could be brought closer. So taking a repeated measurement was just because it was very hard to ensure that the ruler is vertical. But still a single measurement could be accepted here. So x2, she did the first attempt. She also did again x2 the second time, second attempt. So for the first attempt, she recorded 41.9. And for the second attempt, she recorded 42.0. Of course, this is just making judgment, you know. And when she obtained the average, she decided that the average is 42.0 in centimeters. So those are the values that she recorded. But the change in, you notice that x1, x2, and x1 are very close to each other. The difference is very small, which would imply that there is a large percentage uncertainty in x1 minus x2 because the difference is very, very small. Okay, so carefully remove the pipe and mass hanger. The mass will be very hot and pour the hot water into the sink. Calculate x1 minus x2. So she calculated x1 minus x2, and that was 43.2 minus 42.0. And her difference is 1.2 centimeters. So she wrote here 1.2 centimeters. Estimate the percentage uncertainty in your value of x1 minus x2. So in using a ruler, we expected the least count to be approximately 1 millimeter for every ruler. But when you take repeated measurements, of course, the absolute uncertainty increases. So if you decide to just use theoretical values for the absolute uncertainty. Then for a meter ruler, the absolute uncertainty is supposed to be between 2 and 5 millimeters if it is used several times. So I expect that as a teacher, you should encourage your students that every time they use a ruler for a measurement and they use a ruler to repeat the measurement, then the absolute uncertainty goes on increasing. And for a ruler, if it is used once, the absolute could be very close to 1 or 2 millimeters. But if it is used many times, the absolute goes on accumulating. So if we think of a ruler being used to measure x1 and there's an uncertainty of say 0.2 millimeters, I mean 0.2 centimeters. If this is a ruler, you are measuring x1. You look at the ruler this side, there's a most likelihood of an uncertainty. There's another likelihood of an uncertainty this side. Then you repeat using a ruler to measure x2. So it means the uncertainty continues increasing. So I expect that the absolute uncertainty for a ruler is going to be in the range at 0.2 centimeters to around 0.5 centimeters for a meter ruler or any ruler when it is used many times. So my student chose the absolute uncertainty to be 0.4 centimeters because she considered an absolute in x1 as 0.2 and absolute in x2 as 0.2 centimeters, and she summed them up. So she mentioned that absolute uncertainty in x1 minus x2 according to her was 0.2 plus 0.2, which she said it is 0.4 centimeters. Then she calculated the percentage uncertainty in x1 minus x2. It was 0.4 centimeters divided by 1.2 centimeters, then times 100. So let's check. So this is 0.4 divided by 1.2, then times 100. This gave her 33.3%. You see, this is a large percentage uncertainty. So the percentage uncertainty she wrote there was 33.3%. Alternatively, you could also use half of the range. You could use half of the range, but this one means you need the range in x1 minus x2. So you could choose just one set of values. You could choose one set of values and you get half of the range. So you could use x1 here and x2 here, you get the value. You use x1 here and x2 here, you get the value, then you get half of the range of those two values. So that would give you again a percentage uncertainty. But remember, the answer here may not be exactly the same, but the method is what is very important. If you're using half of the range is very hard, just remember that for a ruler, the absolute uncertainty is between 0.2 centimeters to 0.5 centimeters, and to always any value in that range, 0.2 centimeters to 0.5 will always be accepted. So you just take one value in that range as the absolute, which is going to give you the percentage. Then measure and record the length L of the shorter pipe. So they had now to repeat the experiment with a shorter pipe by measuring its length. And my student again repeated the measurement. Every time you take a repeated measurement, draw a nice table to give a good impression to the examiner that you know what you're dealing with. So she did the first attempt in centimeters. She did the second attempt in centimeters. It was a shorter pipe, which is around 7 centimeters. So the first attempt, she said, is 7.4. Then she changed, I think she rotated the pipe. It was maybe not very uniform, and she measured 7.2 centimeters. So she recorded her average as 7.3 centimeters. Any measurement from the ruler should be to 1 decimal place in centimeters. Repeat B, Roman 1, Roman 2, and Roman 3 using the shorter pipe. So we just repeated for x1 for shorter pipe. And the second value for x1 which she recorded was 42.1 in centimeters for a shorter pipe. Then the temperature she used was 60. No, she used 62. So the temperature she used here was 62 degrees Celsius. So the temperature she recorded is 62 degrees Celsius because the thermometer measures to the nearest whole number. So she recorded 62 degrees Celsius. Then she repeated for x2 and her value of x2 is 41.9 centimeters. So she got x1 as 41.9 centimeters. So of course the change in length is very, very small. That's why we have even a larger percentage uncertainty. So the marking point here is just that the second value of L is supposed to be less than the first value of L, so the rest is fine, whatever measurement you obtain. So finding x1 minus x2, she got 42.1 minus 41.9. So 42.1 minus 41.9, and she got 0.2 centimeters. So here she has 0.2 centimeters as the difference. Okay. So we notice that there's a smaller difference in x1 minus x2, which gives a larger percentage uncertainty. So that is another limitation. It is suggested that the relationship between x1, x2, L, T, and T naught is given by that. So if we make K the subject, so K is going to be L into T minus T naught divided by x1 minus x2. Use your data to calculate two K values. So the first K value, K1, L. We use the first value of L was, our first value of L was 12, I think 12 point something. L was 12.2 centimeters. So this is 12.2 centimeters. Then the change in temperature, T minus T naught. The initial T, the first T was 67. Then T naught, room temperature was 24, I think. Room temperature was 24. So 67 minus 24. So this is 67 minus 24. Then divide by x1 minus x2. For the first attempt, x1 minus x2 was 1.2. So this is going to be 1.2. So divide by 1.2. Of course, this is in centimeters. This is going to be in degrees Celsius. So the answers are going to be in degrees Celsius if the units are asked. Because this is centimeters, this was centimeters, this is degrees Celsius. So centimeters and centimeters would cancel. Okay, so just check this. 12.2 times 67, no, room temperature was 24. 67 minus 24, so that is 524.6, 524.6, and we divide this by 1.2, that is 437. I'll just record 437, or you can even record 440, depending on what you want, because the smallest number of significant figures is 2, so the answer can have 2 significant figures or more, but not less than 2. So I can even record 437 or 434. You can record 437 or 440, but not 400. It is not possible. So you can record this or more significant figures, but not less than 2, because this is 3 significant figures, this is 2 significant figures. The smallest number should be 2 significant figures, because here the smallest number in the raw data is 2 significant figures. Then K2, L was, for the second attempt, K2, L was 7.3. So L is 7.3 centimeters. Temperature is 62 minus T naught, which was 24 degrees Celsius, divided by x1 minus x2, which is 0.2. So this is 0.2 centimeters. So we shall check this. 7.3 times 62 minus 24. So this is what we get, divided by 0.2. So you see that there's a very large difference here. So there's a large difference here. So this student go to 1000. Second value of K is 1000. I hope I calculated this correctly. 7.3 times 62 minus 24 divided by 0.2. So this is 1387, which is extremely big. Okay. So justify the number. I really don't like to use this result. I have to choose the result of another student, because this is a large percentage difference. Okay, I'll use another student's results because this is a large percentage difference. So from here, another student here got 42.1, and here the student got this is 40.0, 40.2. Okay, so this student got 40.4. Let me use this one here. 42.1 and 40.4, because I don't want a very large percentage difference. 40 point. So I've picked another student so that I have a better, at least a smaller percentage difference. So this student's x2 is 40.2 centimeters. So this means this student's difference in x1 minus x2 is going to be 42.1 minus 40.2. Always you don't need to get worried about the value you get, because the examiner will be so much interested in the method rather than the answer. But of course, getting a percentage difference above 100 would really be very not nice at all. So this student here has 1.9. So let me check this. 7.3 times 62 minus 24 divided by 1.9. So this has 146. So this is 146. Okay. So let's find the percentage of course, these are the two K values. They didn't ask for the units. So this is just to show you how you just calculate your K values. So that is how you calculate your K values. So the next question asks us to just find the number of significant figures that you have given for your K values. Why have you given 3 or 2 significant figures? You look at the raw data. The smallest number of significant figures there is 2 significant figures. So you will say since x1 minus x2 is to 2 significant figures, 2 significant figures, and of course we have 3 terms here. We have t minus t naught. So since x1 minus x2 is to 2 significant figures, t minus t naught is to 2 significant figures, and we have L is to at least 2 significant figures. So although this is 3, this is 2, so the minimum is 3. And L is to at least 2 significant figures. I'm saying 2 significant figures because this is 2, the other one is 3. So, and L is to at least 2 significant figures. So to maintain accuracy, K should be to at least 2 significant figures. To maintain accuracy, so to maintain the same degree of accuracy, K should be to at least 2 significant figures. So the smallest number of significant figures should not be less than 2, since the smallest number of significant figures in the raw data that we have used to calculate K is 2. So to maintain the same degree of accuracy, K should be to at least 2 significant figures, but not less than 2 significant figures. So I can write 2 or 3, but not less than 2. It is suggested that the percentage uncertainty in the values of K is 20%. Using this uncertainty, explain whether your results support the suggested relationship. Okay, so we just find the percentage difference in K value. Since this time they have given us a criterion, so we just find the percentage difference in K values. So we say percentage difference in K values is going to be equal to, so I will say 437 minus 146. I may divide by the highest, or you can divide by the average. So I would say divide by 436. Then I will multiply this by 100. So that is percentage. So you can divide by the highest or by the average, no problem. So this will be 437 minus 146 divided by 436 times 100. So this is going to be 67%, approximately 67%. So this means there's a large percentage difference in the K value. So you will say, since percentage difference in K values is greater than, they suggested 20%, so it is greater than 20%. So K cannot be considered constant. K cannot be considered constant, and the relationship is not supported. So because the percentage difference in K values is now way over 20%, we can't consider K to be constant. So the relationship is not supported. So that one will give you that mark. Describe 4 sources of uncertainty or limitations of the procedure of the experiment. So of course, since we have calculated 2K values, the first limitation is always the same. Since we have 2K values, the first limitation is always the same. But remember, sometimes we calculate 3K values. So just modify the limitation in that case. So we shall simply say 2 readings are not enough. 2 readings are not enough to draw a valid conclusion. Because we have calculated only 2K values, it means we have only 2 readings, so that they are not enough to draw a valid conclusion. So you take more readings and plot a graph. Take more readings and plot a graph. Alternatively, you could say take more readings, obtain more K values, and compare them. You would say take more readings, obtain more K values, and compare them. So take more readings, obtain more K values, and compare them. That's how we answer that part of the limitation. Okay, so we have also seen that there was a difficulty in measuring X because as you bring the ruler closer to the rod, you knock the rod and it moves. It is hard for you to hold the ruler vertical. It is hard for you to hold the ruler without the hand shaking. All that relates to measuring X. So difficult to measure X, whether X1 or X2. So difficult to measure X. Since the rod moves, when you bring the ruler closer, you may knock the rod and it moves, or you can say the ruler moves because your hand shakes. The ruler moves. You could say the ruler is not vertical. It is hard to ensure that the ruler is vertical when you're measuring a vertical distance by placing the ruler on the bench. So you can say the ruler is not vertical. The rule is not vertical. I don't follow the lines because I want to write more limitations and more methods of improvement. So that's why I don't follow these lines. Okay, so how can this one be solved? For the shaking of the hand or the moving of the ruler, you can clamp the ruler. You may clamp the rule. For the ruler not being vertical, you could use a plumb line. Use a plumb line. The plumb line is like you just attach a mass onto a string. Then, of course, you will need still a clamp. So use a plumb line. You can check that the ruler is vertical by using a plumb line. That would help in reducing that limitation. Number 3, the difference between x1 and x2 was too small. This gave a large percentage uncertainty in x1 minus x2. So we say x1 minus x2 is too small, giving a large percentage uncertainty in x1 minus x2. So because the difference is very small, this gave a large percentage uncertainty in x1 minus x2. If we want to reduce that percentage uncertainty, then what could we do? So to reduce that percentage uncertainty, we could have increased the length of the rod. We make it longer so that it can cause a bigger extension, or it can cause a bigger stretch, or it can undergo a bigger depression than the ones that we saw in the practical. So you could increase the length of the rod. Alternatively, we could just make the pipes longer, or increase the length of the rod or the pipe. So if the pipe is longer, we expect at least a bigger increase in length, so that the difference in x1 and x2 could be bigger. Okay. The number 3 or number 4, we can suspect that the string could change length. Of course, when the pipe is attached on the strings, according to the strings we used, the string changes length when wet. So the string changes length, slightly changes length when wet. Some strings in the laboratory, when they become wet, they become easier to stretch. So the string changes length when wet, yet we are interested in the extension or in the expansion of the pipe alone. So how do we solve that? If we don't want the string to change length when it is wet, we use nylon. Of course, nylon, if you use nylon, we don't have such a limitation. So use nylon string, or you can use a plastic string, you can use a metal wire. Use nylon string or a metal wire. So on tying those pipes, instead of using a string, which is an ordinary string that can stretch when it is wet, you could use nylon. Nylon does not stretch even when it is wet. Or you could use a metal wire. Then, I think you might have noticed that the room temperature is not constant during the whole experiment. So the room temperature T0 changes during the experiment. Room temperature T0 changes during the experiment. Room temperature slightly changes during the experiment. And how would you solve that? To avoid room temperature from changing, or you cannot stop room temperature from changing, but the only way you can minimize the uncertainty due to that, you measure T naught just before you add the water. Instead of measuring, take some time, then add water and measure T instead of measuring T naught just before adding the water. So you would measure T naught. You would measure the room temperature again before you just add water. Measure T naught just before water is added, before the hot water is added. Okay, and maybe lastly, because this is water, you may also notice that the temperature at the bottom may not be the same as the temperature at the top. It might also have been hard to measure the length L because the pipe is curved. And also notice that L, when you look at the diagram, L is not the distance between the ends of the pipe. When you look at the diagram here, L is the distance between the pipe, right? But then when we are measuring the extension, because we are actually measuring, it's like we are measuring from here up to here where the strings are attached. So we could say L is not the distance between the holes where the strings are attached, because the pipe is supposed to stretch from this point to this point so that the pipe stretches. The other ends after the holes will not expected to stretch. So L is not the distance between the holes. L is the distance from the ends of the pipe. So that makes the answer not to be very accurate. And since it is just a pipe, it could be a limitation to measure the length L of the pipe since it is curved. So I would say difficult to measure L because difficult to measure L because the pipe is curved. It is difficult to measure L because the pipe is curved. Or you could say L is not the length or is not the distance between the holes. Yet for extension, L should be the distance between the holes. So if you say it is difficult to measure L because the pipe is not straight, so you could use a tape measure. Use a tape measure instead of a ruler. Use a tape measure. Instead of a tape measure, you could also use a string and a ruler. You put a string along the length of the pipe, then you transfer onto the ruler. You could use a string and a ruler. Or you could make a L. Make a L the distance between the holes instead. So instead of taking L to be the distance from one end of the pipe to the other, yet the holes, the strings are attached here and here, you could instead make L to be the distance between the holes instead of being the length of the whole pipe. So make L to be the distance between the holes instead. Then maybe I can add one which I've just mentioned about the temperature of the water, which varying with the position in the measuring cylinder. So difficult to measure T, difficult to measure T as the temperature of the water varies with the position. The temperature of the water varies with the position in the measuring cylinder. Of course, the temperature on the top of the water is not the same as the temperature at the bottom of the water. And of course, even when you put in the thermometer, it is going to touch the sides of the cylinder, which affects the temperature. And you cannot measure, you may not be able to measure X and T at the same time. All those are relating to almost the same thing. So temperature of water varies with the position in measuring cylinder. You can say the thermometer touches the sides. Thermometer touches sides of the cylinder. You could say you cannot measure X. Of course, you must measure X and T. When you first you first measure T, when you first measure X, then T. By the time you measure T, X is changing. When you say you first measure T before X, by the time you move to measure X, it will be changing still, because the temperature will have changed. So you cannot measure X and T at the same time. At the same time, since T decreases rapidly. When you pour boiling water into the cylinder, its temperature starts decreasing. Since T decreases rapidly. Okay, so how do we solve that? I may not give methods of improvement for each of these, but they are relating to the same thing. They are relating to measuring temperature T. So one, if you want the temperature at the bottom of the cylinder to be the same at the top, you stir the liquid. That one you know from thermophysics. So use a stirrer for the water. So when you stir the water, you expect thermal equilibrium. We have said the thermometer touches the sides of the tube of the cylinder, so you could clamp the thermometer to avoid it touching the sides of the tube of the cylinder, or you could use thermostatically. It is called thermostatically, not thermostatically controlled water bath. Use a thermostatically controlled water bath. So this one will prevent the temperature from rapidly decreasing. Okay, so that is how you would approach this question. I think you have learned something, at least one or two for this video, and I hope to see you in another video. Do not forget to share, download, subscribe, like, and comment. I'm always willing to reply to all your comments. Until next time, bye bye.